Hello, AP Physics C. Today we're going to be talking about conductors for our electricity and magnetism class. And we're going to start with some properties of conductors. These are general knowledge things that you should memorize that have to do with conductors, and they will answer a ton of questions on your exam. Conductors, the first one, conductors always carry their charge on their exterior surface. So if you have excess charge on a conductor, all of it is located on that exterior. Within the conductor itself, the electric field is going to be 0. And the electric field strength at the surface of a charged conductor will always be constant because of that concentration of charge. Voltage within a surface of a conductor is also going to be constant. That is not 0 and constant. And then if you ever have two conductors that are wired together, the voltage will equalize itself across the surface of all the conductors. Within the conductor, the same voltage that occurs within the conductor is going to be the voltage that is on the surface of the conductor. So these main ideas about conductors are things that you should know. Moving on, I want to talk to you about a Faraday cage, because some of the properties about conductors can be used to make something called a Faraday cage. Before I explain what it is, I want to explain how it's used. Faraday cages are used to separate sensitive electronics from exterior effects. So if you want to isolate something electrically, you put it in this thing called a Faraday cage. And essentially what we're going to do is we're going to put it inside of a conductor. Because the electric field within a conductor is always 0, that means that charge can't move within the conductor due to something that's happening outside of a conductor. So if you have some outside effect, all the effect will happen on the outside conductor and not penetrate inside of the conductor to affect what's inside. What we end up doing is we make enclosures around our sensitive electronics. Think computers, think television, right? You'll see these in front yards when they have transformers. You also see transformers up on like the poles at the back of the yards carrying these metal cases. The reason why they're always made up out of metal is not so much to protect what's inside of them from what's inside from what's outside, but what is inside those things is extremely high voltage, and the cage itself gives sort of a buffer, so that way the high voltage equipment inside of it can't affect what's outside of it. And that's a Faraday cage. So you see them in all sorts of electronics. You might call it like shielding, and it was named after Faraday. Equipotentials. Equipotentials are lines or curves that are shown on some sort of map that show a path where all the potential difference, that's the voltage, is constant. They kind of look like field lines, but they're showing really the other side of it. They run perpendicular to field lines. So electric field lines show how charges would move. Equipotential shows areas of constant potential difference. Whenever you have electric field lines and you are comparing them with equipotential lines, the equipotential lines and the electric field lines are always perpendicular to each other. So it'll run high to low, perpendicular to each other, and the field lines always point from high to low. This one comes up quite a bit, that if you end up on the same equipotential line that you started on, you're just at a different point, the same line, because your potential difference is going to be the same before and after. That means that no work can be done moving between those points. So let's do a couple of examples on equipotentials. The first one, you can see that we have a map here. This map is showing equipotential lines. Starts all the way at the left at positive 25 volts. All the way at the right, you get down to a negative 20 volts. And there's a series of points in here, A through G, that show different positions of interest to us. The first thing they want us to do is to draw some arrows showing the vector direction of the electric field at each of these points. And this goes back to the idea that equipotential lines and electric field lines are always perpendicular. So here, as we're drawing electric field lines based on electric field or electric potential, equipotential lines, they're all going to be perpendicular to that. And you'll see all these red arrows pop up, and each of these arrows is pointing perpendicular to the equipotential lines, and they all show the direction of the electric field at that point. So any charges released in that area would feel forces based on these red arrows. If we're looking at the difference between 2 points in the field that's shown by equal potential lines, each of these lines shows a spot of electric potential. So at point A and point C, the first example, point A has a voltage of 25 volts, and point C has a voltage of 15 volts. So the difference between them is 10. 25 minus 15 is 10 volts. So as you go from A to C, your difference in energy is going to be 10 volts per coulomb. From between B and F, B starts at 20 volts and F is at 0 volts, so you'll end up with 20 volts there. Between C and G, C is at positive 15 volts and G is at negative 10 volts. And that's going to give us 15 minus negative 10 gives us 25 volts. And then this last one is probably the most interesting one between C and D, different points on the same equal potential line though. So as you go between the two, you end up at the same potential difference you started at. So the potential difference has to be 0 volts. And then this last question on equal potential lines, they want to know how much work is done as you move from B to F in this field. From B to F, we've already identified that the potential difference is 20 volts. We know the charge moving is 1 microcoulomb. And we're going to use this equation from our reference tables that says that the energy is equal to voltage times charge. We know the voltage, 20 volts, and we know the charge, 1 microcoulomb. We multiply them together to get an energy of 2.0 times 10 to the negative 5 joules. A lot of times this will be a kinetic energy if it's an object that's allowed to move between the 2 points. Sometime it might represent a certain amount of work that was done by a charge moving between these 2 points to do something other than electric, other than kinetic energy.